Sir,
Yes.
excuse me, sir. I had a doubt regarding the last class.
Huh.
Sir, you said that for linearly, uh, sir, what were the conditions for linearly dependent and independent? Can you repeat those?
Linear. Yes, yes. Actually, linearly means a non-trivial linear combination of vector or solution which which gives gives zero is linearly dependent, otherwise linearly independent. Means if we have the y1, y2, yn given vector or solution, if you write the c1, c2, cn, if you take their sum and if it is equal to, so I'm saying that non-trivial means this c1, c2, cn, right? c1, c2, cn should be non-zero, should
Sir,
be
even
non-zero.
if sir, even if one is non-zero, then also it is linearly
Ha,
dependent, right?
ha. Yes.
Sir,
Means
all should be
at
equal
least,
and
no,
equal
no,
to zero.
at least one of the c1, c2, cn should be non-zero, then it is the ld. If if all are zero, if all are zero, then li. Clear? Clear?
Yes, sir.
So let us start. So we were discussing last time theorem 15 about the general solution of homogeneous differential equation of, right, means of higher order differential equation. So before that we have covered the section 14, three theorems was theorem a. Theorem a state that theorem 14a state that if some condition is given to you, y naught and y naught dash is given to you, and it is for the x is equal to x naught and y dash for the x is equal to x naught, then yx be the unique, then yx be the unique. If condition is given to you, then solution will be the unique. Then theorem 14b state that if we have two solution yg and yp, yg is general solution of reduced equation or homogeneous equation, and yp is particular solution of complete equation. Then y is equal to yg plus yp, yg plus yp be general solution of complete equation. This is the theorem 14b. Then theorem 14c state that if y1 and y2 are solution of reduced equation or homogeneous equation, then their linear combination c1y1 plus c2y2 also solution be also solution of reduced equation, reduced equation. But in 14b, we have said that YG the general solution. YG is the general solution. Here I am saying that only the solution. I am not claiming it is the general solution. So for that we have the theorem 15. So theorem 15 states that let a y1 and y2 be linearly independent solution of homogeneous equation y double dash plus px y dash plus qx y is equal to 0 on the interval ab. Then c1 y1 plus c2 y2 be the general solution. In that case, the linear combination be the general solution of first on AB, in the sense that every solution of the first on the interval can be obtained from 2 by suitable choice of arbitrary constant C1 and C2. So what is the theorem? Theorem states that if y1, now theorem 15, it states that if y1 and y2, if y1 and y2 are solution of homogeneous differential equation y double dash plus px y dash plus qx y is equal to 0, their linear combination c1 y1 plus c2 y2, right? From the 14c, from the 14c be the solution of first by theorem 14c. Now we want instead of the solution, we want it is the general solution. It is the general solution. For the general solution, it is given to you that y1 and y2 must be li, must be li. And what is the characteristic of the general solution? The characteristic of the general solution is from the given solution you can find any solution. That is the characteristic of the general solution. So let yx be any arbitrary solution of the first. So can we get the yx from the given solution? So that you can obtain only when yx is equal to c1 y1 x plus c2 y2 x, then only you can determine, then you can say it is a general solution. Because if yx is arbitrary solution and with proper choice of c1 and c2 you can obtain the arbitrary solution, then we say c1 y1 plus c2 y2 be the general solution. That is our statement. For the proper choice of the for the proper choice of c1 and c2 we can obtain this. So that is the gist of the theorem 15. So for
Sir,
that purpose,
C1 and C2 are arbitrary constants.
c1 and c2 are
Sir, they are basically constants, right? For a particular
arbitrary
equation.
constant. Yes, any other doubt? It is written here, arbitrary constant. So now we are moving to proof of this. So we will prove this theorem using the certain lemma. So in previous class I have told you we have the three terms in general: axiom, lemma and theorem. Axiom is the statement which we assume always it is true. There is no requirement of the proof. Lemma is the theorem. Lemma is the statement which require the proof, and lemma is the statement which is required for the proof of the theorem, and its proof we write, and theorem is the statement for which we write the proof. So here, for proving the theorem 15, we use the two lemmas. We will use the two lemmas. So what is the strategy? We assume here, let y be any means arbitrary solution, any solution of the first on interval a comma b. We have to show the we have to show that constant c1 and c2 can be found, so that yx is equal to c1 y1x plus c2 y2x for all x in closed interval ab. So that I have written here also, right? We have to show that we can determine the c1 and c2, right, arbitrary constant, so that yx is equal to this. So for that purpose, by theorem 14a, by theorem, when these two solutions are similar, it means when we are saying that yx is equal to c1 y1x plus c2 y2x, it means the solution is what? It is the unique. And in the theorem 14a, when we have the unique solution, when some arbitrary conditions are given to you, some condition is given to you, then only we say by the theorem 14 that two solutions are similar or same. So here, by the theorem 14a, we know that solution of the first over all the interval ab can ab is completely determined by its value and the value of its derivative at a single point. So let us assume c1 y1 x plus c2 y2 x is one solution, yx is another solution. Presently we are assuming that both are the different solution. c1 y1 x plus c2 y2 x is one solution of the first one, right? Means this is the solution by the theorem 14c. By the theorem 14c, this is the one solution, and this is the arbitrary solution. This is the arbitrary solution. So we are assuming that they are the two solutions. Are both solution of the first on closed interval ab. Then for some point, let x naught is the initial point. For the some point x naught in ab, we can find the c1 and c2. We can find the c1 and c2 when we can solve this equation. So I am claiming that we have to prove that yx is equal to c1 y1x plus c2 y2x. So for the point in the closed interval ab, we have the arbitrary point x naught. At this point, by chance you assume that this is the yx, and this is the c1 y1 plus c2 y2. For a moment you assume that these are the two different functions. But for this point, what we can have? c1 y1 x naught plus c2 y2 x naught is equal to y at x naught, and c1 y1 dash x naught plus c2 y2 dash x naught is equal to y dash at x naught, at then now for computing the c1 and c2, the determinant of the y1 y2 y1 dash y2 dash must be non-zero, then only this system of equation will give you the unique solution, the value of c1 and c2, when the determinant y1 y2 y1 dash y2 dash is non-zero. So if I am saying that, let it is the x naught. So between the a to b, can we have this condition that at this point this determinant is 0, right? At this point this determinant is not 0. Can we have this thing between the a to b? Can we have this fluctuating thing? For some point it is 0, for some point it is non-zero. So for that we have the lemma. So here, this we have already discussed. So this determinant is known as the Wronskian. This determinant is known as a Wronskian, Wronskian, and we denote it by the W, which is the function of y1 and y2, which is the function of the y1 and y2. Now, so in the first lemma, if y1 and y2 are any two solution of the first on AB, then their Wronskian W is equal to W of y1 and y2 is either identically 0 or nowhere or never 0 on the closed interval AB. So now we have to prove that Wronskian is either 0 or never 0 on the closed interval AB. Means if it is the AB, so either for all point W is equal to 0, or between the AB, never the W is equal to 0, or not fluctuating, not fluctuating. Means for some point it is 0, for some point it is not 0, right? So that is the here logic. So now let us see the proof of this. So we assume that W is equal to what? W is equal to y1 y2 dash minus y2 y1 dash. It is the determinant. So W dash will become y1 y2 double dash by parts you do, and y1 dash y2 double dash, and minus y2 y1 double dash plus y2 dash y1 dash, which gives you y1 y2 double dash minus y2 y1 double dash. And clear this part. Here the y1 dash and y2 dash will cancel out. Now y1 and y2 are the solution of the first. It means it satisfies the equation. So when it satisfies the equation, I am saying that y1 is solution of y1 is solution of the first. It means it will become y1 double dash plus px y1 dash plus qx y1 is equal to 0. y2 is solution of first, so we say y2 double dash plus px y2 dash plus qx y2 is equal to 0. So let's say it is the A, it is B. So in the A, you multiply with the y2 and subtract, right, minus. In the B, you multiply with the y1. So first one will come y1 double dash y2 plus px y1 dash y2 plus qx y1 y2 minus y1 y2 double dash plus px, and this will become px y1 y2 dash plus qx y1 y2 is equal to 0, so this will cancel out, and here we can write y1 double dash y2 minus y1 y2 double dash plus px into y1 dash y2 minus y1 y2 double dash y2 dash is equal to 0. And what is this? This is the W. And what is this? This is the W dash. So we can write it as a dw by dx plus px into W is equal to 0, or
So this is minus. These are negative of dw and w. Yeah, it won't matter, sir, because it's equal to 0.
it is equal to 0, I think. Right? So it will be the dw by no dw upon w is equal to minus px dx. Px dx by you can separate the variable. So when you integrate on both side, it will give you ln w is equal to minus integral px dx plus ln c, or w is equal to c e to power minus integral px dx. So this w, if c not equal to 0, if c not equal to 0, w is w not equal to 0, nowhere, nowhere 0, nowhere 0, since exponential function is never 0. If c is equal to 0, w is also 0, everywhere 0, everywhere 0, since e to power or exponential function is never 0. So this will prove that Wronskian is either Wronskian is either nowhere 0 or everywhere 0 in closed interval AB. There is no fluctuation. There is no fluctuation between the 0 and non-zero value of the W. Then we have now when we say now by the theorem 14c we have that yx is equal to c1 y1 plus c2 y2, c2 y2, and we want c1 y1 plus c2 y2 is the general solution. General solution means for the some constants c1 and c2 we can obtain arbitrary solution yx. So for that we assume that we have to compute the what is the that those value of the c1 and c2. So for those we have the two equations, simultaneous equation, and the c1 and c2 can exist only when the Wronskian or determinant of y1 y2 y1 dash y2 dash is the non-zero, right? So for that we see that Wronskian is either everywhere 0 or nowhere 0. Now in the question, in the theorem it is given that y1 and y2 must be Li, then only we can write this as a general solution. So how the LD or Li is related to the Wronskian? Now the question arises, how the Li means in case of the Li only, in case of Li only, the determinant of y1 y2 y1 dash y2 dash can be non-zero. So next lemma will prove this. So here we have thus the Wronskian of plus conclude this. Thus the Wronskian of any two linearly independent solution of the first is not identically 0. Right, here we have. So in this case, for this statement we require the lemma 2. If y1 and y2 are the two solution of the first on closed interval AB, then they are LD, linearly dependent. Then they are the LD, linearly dependent on this interval if Wronskian W is equal to y1 y2 dash minus y2 y1 dash is identically 0. If W is equal to 0, if W is equal to 0, y1 and y2 are LD. If Wronskian is non-zero, then y1 and y2 are Li. So we prove now we have to prove this lemma. Let y1 and y2 are the linearly dependent. Means it is what we have to prove. We have to prove that y1 and y2 are LD implies W is equal to 0. If W is equal to 0, then implies y1 and y2 are LD. So first we assume if y1 and y2 are linearly dependent. if y1 and y2 are linearly dependent. Now we have to prove that whether the Wronskian is 0 or not. So, in this case, first we will see if the y1 and y2 are the linearly independent, if either of the function is identically 0. If either of the function is identically 0, case first, if you assume case first, let either of y1 and y2 is equal to 0. Identically 0 means they are the 0. So what is the w? W is the y1, y2, y1 dash, y2 dash, y2 dash. I'm saying that let us assume y1 is 0. So it is a 0, y2, 0, y2 dash, it will give you 0. Right? So it will give you w is equal to 0 when y1 and y2 are LD. And you know that if any function is 0, right? If any function is 0, then y1 and y2 will be the LD. Now, case second, let neither be identically 0. Neither be identically 0 means both are non-zero. Y1 and y2 both are non-zero. Both are non-zero. If both are non-zero, so if they are the LD, what is the definition of the LD? One is constant multiple of other. Constant multiple of other. That is the definition of the LD. Let y2 is what? K of y1. So what will be the y2 dash? It is the k of y1 dash. Now, if you compute the Wronskian, y1, y2, y1 dash, y2 dash, so it will become y1, k y1, y1 dash, k y1 dash. And what is this? It is the 0. Right? K y1 y1 dash minus k y1 y1 dash. So it is 0. So here you have proved that if y1 and y2 are LD, then right, then the Wronskian is equal to 0. Wronskian is equal to 0. So here it is also written. Therefore, assume neither is identically 0. Thus, by definition of linearly dependent, each is constant multiple of other. Let y2 is equal to c y1. So y2 dash is equal to c y1 dash. So here we have proved the Wronskian, put in the Wronskian. So Wronskian will come the 0. So it is now we assume that w is identically 0. Now if w is identically 0 means w is equal to 0. If this case is given to you that w is identically 0, in that now we have to prove that y1 and y2 are linearly dependent. So if y1 is identically 0, then the function are linearly dependent. 0 function is always linearly dependent to other one. So case first, if y1 is identically 0, if y1 is identically 0, if y1 is identically 0, then there is no need of proof. Then y1 and y2 are LD. Then they are the LD. So which case we have to take? We have to take the second case. Case second, if y1 is not identically 0, if y1 is not identically 0, if y1 is not identically 0, and what is given to you? W is equal to 0 is given to you. What is the W? W is the y1, y2, y1 dash, y2 dash is equal to 0. So this is given to you. Y1 is not identically 0 and W is equal to 0 on interval on interval a comma b. So if let it is the a comma b, in this we have c and d arbitrary point, any arbitrary interval. If W is equal to 0 between a to b, so it will give you W is equal to 0 for the interval c comma d also. Because if W is either identically either everywhere 0 or nowhere 0 on the interval a b, so W is equal to 0 in the interval c comma d, and this can be written as y1 y2 dash minus y2 y1 dash is equal to 0. If you divide it by the y1 square, y1 y2 dash minus y2 y1 dash upon y1 square is also 0. Why we can divide with the y1? Because y1 is non-zero. Y1 is non-zero, that we have assumed in starting, right? Y1 is non-zero, not identically 0. So y1 is non-zero, we can write it like this. And what is this? This is the d of y2 upon y1 is equal to 0. It means y2 upon y1 will be the k, a constant, or you can say y2 is equal to k y1. So y2 is k y1. So y2 is constant multiple of y2 is constant multiple constant multiple of y1 in interval c comma d, right? C comma d, and y2 dash will be the k y1 dash Now why the theorem, or why the theorem 14a, why we have the unique solution. Unique solution means y2 is equal to k of y1. Both are same. So it is we have the y2 is equal to k y1. And by the theorem 14, by the theorem 14a, by theorem 14a, what is the theorem 14a? If something is unique, right? If something is unique at a point between the or in the interval this, right? So we have the unique solution. Means here by the theorem 14a, y2 is equal to k y1 for, it is true for x belongs to a comma b. For the complete interval also it is true, right? Because theorem 14a state that if at a point it satisfy the if at a point it satisfy the these two conditions, then we have the unique solution. Here it is satisfying in the interval c comma d, it means y2 and k y1 both are similar and both are the same thing. They are the unique, right? For the interval a comma b also, a comma b also. So it will give you y2 is what? Constant multiple of this. It means this implies y1 and y2 are the ld. So what it implies that? It implies that y1 and y2 are ld, implies and implied by Wronskian is equal to 0. So now what we can have the conclusion? Now we can say we can determine the c1 and c2. We can determine the c1 and c2, right? C1 and C2 are arbitrary constant, which gives you y is equal to C1 y1x plus C2 y2x, where y1 and y2 are the Li, or Wronskian is identically non-zero, or means Wronskian should be non-zero. So that is the conclusion. So that is the proof of the complete theorem. Any doubt in this part? Here also the same thing written. Y2 and ky1 have the equal value in CD. They have equal derivative as well. Hence, from the theorem 14a, y2 is equal to ky1 for x in a comma b, which proves the linear dependency. Hence the theorem. Means for the general solution. Now, what is the conclusion? For the general solution, y1 and y2 must be Li. Then only it can be the general solution. Otherwise, only the solution. Means there is a two statement of this type. Theorem 14c. Right? If y1 and y2, if y1 and y2 are solution of first, if y1 and y2 are the solution of first, then C1 y1 plus C2 y2, C2 y2 is also solution of first. Theorem 15a, y1 and y2 are the solution, y1 and y2 are the solution, and Li, then C1 y1 plus C2 y2, C1 y1 plus C2 y2 is general solution, is general solution. That is the theorem 15. And
Sir,
that general solution we require for writing the yg plus yp. Yes, now
sir, the theorem 14c is for homogeneous, right?
both are for homogeneous. I am saying that if sin x is the solution of any equation, y double dash minus y is equal to 0. If sin x is the solution of this equation, let us first verify. Y is equal to sin x, y dash is equal to cos x, and y double dash is equal to minus sin x. So plus. Let sin x is the solution of y double dash plus y is equal to 0. Then y is equal to k sin x. K sin x is also solution of y double dash plus y is equal to 0. Is also the solution of this, right? So it means sin x plus k sin x is a solution. So it will give you k plus 1. Sin x is solution of the first. So it cannot give the all solution. It cannot give the all solution because sin x, k sin x, their derivative cos x, k cos x, that is the Wronskian, is equal to 0. So we know that k sin x is what? K sin x is what? K times of the sin x, constant multiple of this. So both implies the sin x and k sin x are the LD. But for the general solution, they must be the Li. They must be the Li. So if you assume y is equal to cos x, y is equal to cos x, it is also solution of y double dash plus y is equal to 0, right? So if you take, so you can say that cos x is not constant multiple of the sin x, or cos x and sin x are the Li, or you can say that, sin x, cos x, cos x, their derivative minus sin x it is not equal to 0. It is not equal to 0. So it is the minus 1. So it is not identically 0. So we can say sin x and cos x are li solution. They are the li solution. So c1 sin x plus c2 cos x is general solution of general solution of the first. That is the logic. Clear? What is the difference between the theorem 14 and 15? Any other doubt? Let us understand this by some question. Still you have a doubt, you can ask. Any other doubt? So that y is equal to c1 e to power x plus c2 e to power 2x is general solution of y double dash plus 3y dash plus 2y is equal to 0 on any interval, and find the particular solution for which y0 is equal to minus 1 and y dash 0 is equal to 1. Right. So here we have the so it is given to you y is equal to c1 e to power x plus c2 e to power 2x is the general solution of this. So for the general solution, first what we have to see, for the general solution, first what we have to see. Yes, what we have to see.
if it is li or not.
Yes, it is a li or not. First we have to see whether the y1 and y2 are the solution or not. First we have to see whether the y1 and y2 are solution or not. So here if you will see, what is the equation? So here we have y double dash minus 3y dash plus 2y is equal to 0. And y1 is what? Y1 is the e to power x. Y2 is what? E to power 2x. So y1 dash e to power x, y1 double dash e to power x, y2 dash 2 e to power x, and y2 double dash it will become the 4 e to power 2x. So when we put y2 double dash e to power x minus 3 e to power x plus 2 e to power x, so it will give the 0, means it satisfies the solution. Here we have the 4 e to power 2x minus 6 e to power 2x plus 2y. 2y means 2 e to power 2x. 2 e to power 2x, that is equal to 0. So it also satisfies the solution. So if it is the solution, then y is equal to c1 e to power x y1 plus c2 e to power 2x be the solution. Be the solution. Then it is the solution. Now for the general solution, we have to see whether one is constant multiple of other or not. So e to power 2x is not a constant multiple of e to power x. Implies e to power x and e to power 2x are not constant multiple of each other of each other. So this implies that e to power x and e to power 2x are ld or by the Wronskian y1 y2 y1 dash y2 dash
Sir, they are
e
li,
to power
right?
x, pardon. हाँ
Sir,
li
they are
li
li.
हाँ li. So e to power x, e to power 2x, e to power x, 2 e to power 2x. So this will give you 2 e to power 3x minus e to power 3x, that is the e to power 3x not equal to 0. If it is not equal to 0, this also implies that y1 and y2 are li. So by the theorem 15, by theorem 15, c1 e to power x plus c2 e to power 2x is general solution, is general solution, that is the yg. Now they are saying that for what value, or find the particular solution for which y0 is equal to -1, y0 is equal to -1, and y dash 0 is equal to 1, y dash 0 is equal to 1. So let's say it is the yg. So yg dash will become c1 e to power x plus 2 c2 e to power 2x, e to power 2x. Now when we put the first condition, x is equal to 0, so it is the -1 and c1 plus c2. And when we put in the second equation, so it will be the 1, and it will give you c1 plus 2c2 plus 2c2. So now we have the two values, right? Two unknowns, c1 and c2, and two equation. So from here we can compute the value of the c1 and c2. So c1 and c2 will come
-3 and 2.
minus 3 and 2. So now it will become the particular. So c1 is the -3 e to power x plus 2 e to power 2x. That is the particular, or that is the means that under some condition you have determined this. So that is the way to determine the general solution and the particular solution. Consider the two function. It is very important question. Please see carefully. Consider the two function fx is equal to x cube and gx is equal to x square mod of x on the interval -1 to 1, so that their Wronskian w is vanishes identically. Fx is equal to x cube, right? First we have to show that their Wronskian is 0. So we assume fx is equal to x cube, gx is equal to x square mod x. So at x square mod x can be written as minus of x cube in the interval -1 to 0 and is equal to x cube in the interval 0 to 1. So when we compute w is equal to f g f dash g dash, so this will become x cube minus x cube 3x square minus 3x square. So it will give you 0, vanishes identically, right? Vanishes identically. So you can see here, I vanishes identically in the interval when for all x belongs to -1 0. It is identically 0 for all x belongs to 0 to 1. Either you take the x from -1 to 0 or 0 to 1. Right here we have taken the minus x cube from here, and here we have taken the plus x cube, right, from here. So you can see from -1 to 1, w is identically 0. Now so that f and g are not linearly dependent. What the theorem state? That if Wronskian is equal to 0, then they must be LD. But here I am saying that Wronskian is 0, then also they are not LD. So for the LD, first what we have to see, let for a given constant C1 and C2, we have linear combination C1F plus C2G is equal to 0. So by the definition, if non-trivial linear combination of two vector, two solution, two function is equal to 0, then we say it is the LD, otherwise we say it is the LI. So here we can write C1 x cube plus C2 x square mod of x is equal to 0. So this can be written as C1 plus C2, means this can be the minus x or x for the x belongs to minus 1 0, and for the x belongs to 0 and 1, 0 and 1. Clear? So this will become C1 plus C2 is equal to 0, C1 minus C2 is equal to 0, 0. So it will give you C1 is equal to C2 is equal to 0, means this implies Li. This implies Li.
Sir,
Now
can you
the
repeat
question is,
part B? Sir,
pardon?
can you repeat? Sir, can you repeat part B?
Here I am saying that I am taking the linear combination C1F plus C2G is equal to 0. C1F is the x cube, C2G is the x square, mod of x is equal to 0. So this will become C1 x cube minus C2 x cube is equal to 0 when x belongs to minus 1 comma 0, and this will become C1 x cube plus C2 x of cube is equal to 0 when x belongs to 0 comma 1. So x cube we can take any value, so it can be written as C1 minus C2 is equal to 0 and C1 plus C2 is equal to 0. So this will imply, this will give you C1 is equal to C2 is equal to 0. So C1 and C2 is equal to 0, it means non-trivial, trivial, it means the trivial, right? Trivial implies Li. So here we can say F and G are Li. F and G are Li. Or earlier we have proved that W is equal to 0. W is equal to 0. Now what is the theorem statement? Theorem 15 statement. Just one line. What is the theorem 15 statement? If W is equal to 0, if W is equal to 0, then F and G must be the LD. But here F and G are coming the Li and W is also coming the 0. So it contradicts the theorem 15. That is the question. It contradicts the theorem 15. So do A and B contradict the lemma 2? If not, why not? So in the lemma 2, what is the main condition? What is the y1 and y2? What is the F and G? F and G there was were the solution of second order homogeneous equation. But in this question, F and G is not a solution. They are the arbitrary function. They are not a solution of any homogeneous equation. That's here written. Since F and G are not solution of differential equation, they are only arbitrary function. That's why it is not contradicting the lemma 2. Lemma 2 is true only for the second order difference, means for the differential equation only. Clear? So that is theoretically very important question. In next class we continue this. This is also very important question to understand the present theorem. So in next class we continue. Still, if anybody wants anything, you may ask. Otherwise, from my side for today, so. Thank you all.